Hello, everyone. This is my first screencastify. We are going to look at work today. Work is a force causing the displacement of an object. The unit of work that we're going to look at is going to be foot-pounds, which is literally the number of feet moved times the force used to move it. So here's kind of an example I have. We have, let's see if I can. Here we go. We have a 20-pound force moving 1 foot. That would be 20 foot-pounds of work because the force is 20 pounds going 1 foot, so 20 foot-pounds. And if it were to go 3 feet, like down here, still 20 pounds, the total work needed would be 60 foot-pounds of work. So if the force is going in the same direction as the distance, it's just simply the force times the distance. Now, as it gets a little bit more complicated when you have different forces at different angles, we're going to use the projection of vectors formula that has been used in the past. And with a couple adjustments, it becomes work equals the dot product of the force vector times the dot product of vector AB. Another possible formula is going to be the magnitude of the force times the magnitude of vector AB times the cosine of theta, where theta is the angle between the force and the direction of the vector. So the important things to know here, the F is the force vector. That's like what's actually being applied to the object. And AB is the actual vector of the object. So where it starts and ends, what that vector looks like. So work can be found by doing the dot product. And what that answer is giving you is kind of like this, the total force used for a specific distance that the object needs to travel. Okay, let's go to the next page. What I'm going to do here is just go through all the even problems. And at the top of the page, I just kind of rewrote the formulas for each time we do a problem. So the first one comes to us for problem 50. So find the work done by lifting a 100-pound bag of potatoes 3 feet. A visual of this. We have a force. The force vector would be a 100-pound bag going straight up. And the reason why it's going straight up is because you are actually lifting it upwards. So the force is going directly north, you could think of it as. The vector, because it's going up 3 feet, the vector of the object is going from 0, 0 to 0, 3. So the two vectors in this problem are 0, 100 for the force and 0, 3 for vector AB. When you're doing these, you have a choice between two documents to use. Or two formulas to use. You could either do the dot product one or the magnitude formula. In this problem, either one works. The angle between them would have just been 0 degrees, so you would have done cosine 0. The magnitudes are 3 and 100, so you would have gotten 300 pretty quickly there. For the sake of just showing you how the first formula works, though, I chose the first formula here. The dot product of the two vectors gets you 300 as well. And ultimately, hopefully it makes sense, an answer of 300. If you're moving a 100-pound bag, that would be the force. 3 feet, the work would be 100 times 3. Okay, moving on to the next even problem, 52. Find the work done by a force of 24 pounds acting in the direction of 4, 5 in moving an object from 0, 0 to 5, 0. So now what's happening is we have this force vector, and we're going to move the vector over this direction. So kind of like with what we did, essentially what we're doing is we're finding the projection of this vector onto this and then multiplying it by the amount that it's moving. Rather than doing that each time, we can just choose one of the formulas up here. So in this specific problem, the formula I'm going to use is going to be F times AB cosine theta. So I'm going to use this formula right here. The magnitude of F is 24 because that is the actual force number there. The magnitude of AB is 5, so it's going to be 24 times 5. The angle, if you think of this as just a standard right triangle here, this theta made between the vector this way and the force vector is going to be inverse tan of 5/4, and that gets you 51.34 in the calculator. Plug it in, we get 74.96. So you could have used this other formula, the force vector times our dot product AB, and it wouldn't have been that bad either. You would have had to have made this into a unit vector, the 4, 5, multiply that unit vector by 24, and then once you have that transformed vector with that force, then you would have a dot product with that vector and the vector 5, 0, which is what 0, 0 to 5 zeros vector would have been. And you would have gotten the same answer of 74.96. Oh, that is how you do problem 52. Okay, moving on to 54 now. So we have a work done with a force of 50 pounds acting in 2, 3, moving an object 5 feet from 0, 0 to some point on the line y equals x. So you can see it's getting a little more complicated now. Let me show you the diagram here to kind of explain what this is. So this diagram here, the u vector is 2, 3. The v vector is just the line y equals x. So it's kind of makes a 45-degree angle with this. The reason I knew that that u was higher is because if you go to the point 2, 3, that point is above the line y equals x. So I knew the vector had to look something like this. I also can kind of see that this angle is going to be quite small between those two vectors. So the formula I decided to use is the magnitude of f times the magnitude of AB times cosine theta again. The reason I chose to use this formula is because the magnitude of the force is already given to us. And it says it's moving 5 feet. So that is the magnitude of AB. So 2 out of the 3 things are already provided for us in the problem. And all we have to do now is just find this theta value. In order to find theta, you want to go back to that formula that we did at the beginning of the chapter, where theta equals the inverse cosine of u dot v over the magnitudes multiplied together. So you don't need to actually get the new versions of u and v. You can just use the ones given in the problem. So 2, 3, and then I just chose the easiest point that's on the line y equals x, which is 1, 1. It turns out that if you do 2, 2 or 5,000, 5,000, you'd still get the same exact ending angle, 11.31 degrees, regardless of which point you choose on vector v. So you do the formula out, you use your calculator, get 11.31 as that angle, and then you know everything you need. You know the magnitude of f, you know the magnitude of AB, and now you just found out 11.31. Plug it all in, and there's our answer, 245.145 pounds. And the final one. So here's the two formulas again. And here we are. So this time, they tell us the angle between a 75-pound force, so that's going to be one of the forces, and AB is 60 degrees. So that tells us theta right there. And this will be the magnitude of F. So already we have the force, the magnitude of the force, the theta, and all we need to do now is find out the magnitude of AB. So the magnitude of AB can be done just by finding out the actual vector that would go from A, -1, 1, to B, 4, 3. And if I do a little sketch of this, or if you do, you could find out that that vector is 5, 2. The magnitude of vector 5, 2 is square root of 29. Now that I know that, all I have to do is put in the FAB cosine theta, F75, AB rad 29, cosine 60, plug it into the calculator, and we get 201.94 foot-pounds worth of work. All right, so that's how to do the even problems. The odd ones that are directly before them are the same exact setup. So if you want to know how to do 55, take a look at how I did 56, and then you can check the answers in the back of the book. Please feel free to email me any questions or put them, even better if you put them into the Schoology discussion set up for today. All right, so good luck.